Today we're going to be doing some more difficult questions with permutations, and we're going to start with probably the hardest one because this is a very good learning opportunity for lists that don't necessarily have what we call edges. So how many ways can we arrange 6 people at a circular table? We're going to do this problem the regular way first and say how many ways can we just arrange 6 people in a list. And we know that there's going to be 6 ways to arrange the first person, then there's 5 ways to choose the second person, 4, then 3, then 2, then 1. So in a list, or let's say, I don't know, let's do a long table here where we have 6 people here. This is the correct amount of people for this scenario. However, that's not what we're after. We are after a circular table where we have an order like this. So, really, there are 6 factorial ways of arranging people around this table. So that is true. However, if we pick, in this case, what we call an anchor position, we're going to pick the top position just because it's convenient. Then what we have is we've designated a sort of edge for our problem. So we put a little imaginary line here, and we say, okay, this is the edge of our table. And then we say, how many ways can we arrange the rest of the people? Now, this might be a little bit unintuitive, because now we're boiling down the problem to a 5 factorial. So another intuitive way of seeing this is saying, well, what if we still had the 6 people and we arranged them like that, but now we consider the fact that this first person can start at 6 possible locations, and as long as the order stays the same, if everyone shifts over 1 position, it is still the same seating arrangement. It just happens to be that they're in different seats. But we wouldn't know that because the table is circular. So we can divide this by 6 and get 5 factorial after canceling. So this is the same answer, 2 different methods to getting that answer, but they work both the same. So here's where the problem gets a little bit more interesting. Suppose we have those same 6 people, except 3 of them are men and 3 of them are women. And we want it so that the men and women alternate. So if we draw this picture here, we have a man, a woman, a man, a woman, a man, and a woman. Okay, so this seems a little bit more difficult to figure out what to do here. So let's index them so we know what's going on. We have man 1, woman 1, and then there's 3 of each. So we want them to alternate. So we say, well, on the first man, there's 3 ways to do him, 3 ways to do the first woman, and then we have 2 for the second man, 2 for the second woman, and then there's 1 for the last man and 1 for the last woman. So what we have here is we have 3 times 3 times 2 times 2 times 1 times 1, which is 9, 18, 36 ways. But this isn't quite correct, because if they all shifted over a few seats, then it would be the same arrangement. But the question is here, do we divide by 6? Well, this is a little bit more difficult because we're not dealing with 6 individual people, we're dealing with pairs of people. So we have this sort of pair right here. We have these pairings of people. And when they move together. So really what's going on is there's a pair 1 position, a pair 2 position, and a pair 3 position. And they all just shift over 1. So really we divide this by 3 to get 12 ways. Now this might be a little bit confusing, so let me show you how my other method that I explained first in the previous question also gives us a nice answer here. I will erase this pair table, and I will do this again. We are going to pick an anchor position A. A is always going to be times 1. Now what we're going to do is we're going to say, well, this is the opposite sex 1. This is going to be the same sex 1, the opposite sex 2, the same sex 2, and the opposite sex 3. So we're ignoring the whole man and woman thing, and we're saying, is it the same as the anchor, or is it different than the anchor? And we can see here, it's a little bit nicer to solve for, because we have 3 ways to choose our first O in the first one. Then for our S1, we have 2 ways. Then 2 ways to choose O2, 1 way to choose S2, and 1 way to choose O3. And here, we get 3 times 2 times 2, which is equal to 12 ways, which is the answer we want. Now, why does this work? This works the same way as my pair table worked, because we pick an anchor position and then we're moving it around to account for all the different seedings that could have possibly happened. Essentially, we want to make a list that starts at A and ends at this O3, so we just chop it up and then we move the anchor position around. Either way works. You might find one of these explanations more intuitive than the other, that's why I'm giving both. If there are any better explanations of this, I would love to see them in the comments below, because this is one of those things that are very difficult to wrap your head around when you first learn, and there are probably other ways of looking at this that some person has come up with that just hasn't written anything in a textbook, because giving intuitions in a textbook is a very difficult thing to do, so I would love to see another method of explaining this that works really well with circular tables. And of course, these tables can have different shapes, and along with that comes different conditions, so perhaps I'll do that at some point. Anyways, let's move on to a more mechanical problem, because the formula is definitely very important when we deal with lists that don't use all of the elements. So, evaluate 6,3. Of course, we want to write at the bottom that P of n choose k is n factorial over n minus k factorial. So here with P6,3, we just plug things into our formula here. So this will be 6 factorial over 3 factorial. And when we expand this out, we're going to get 6 times 5 times 4. I'm going to expand the whole thing out for the first problem, because I think it might be more beneficial for some people who couldn't quite grasp the concept last time. So here we've expanded top and bottom out. And now what we do is we cancel like terms. So the 3 cancels on top, the 2 cancels, and the 1 cancels. So now we're left with 6 times 5 times 4, which is just going to equal 120. Now this is the same thing as saying 6 times 5 times 4 times 3 factorial, all divided by 3 factorial. It's just that we expanded this 3 factorial to be this top part, and the same thing at the bottom, just to show the exact process that was going on here. Okay, now let's do this next problem here. Again, we just do the same concept, so this is going to be 12 factorial over 12 minus 3, which is 9 factorial. So when we expand this on the top here, we're going to get 12 times 11 times 10 times 9 factorial, all over 9 factorial. Oops, that looks like 91. So when the 9 factorials cancel, we get 12 times 11 times 10, which should be 1,320. So these are just some very simple mechanical problems, but it's good that you know how to apply the formula, because it will save lives. mainly because if you have a question where you have to figure out permutations, and someone's life is really dependent on how to seat people at a table, and they need to know how many ways, because they're about to win some lottery that requires them to know, you're going to make them a few $1 million, and that's going to make them very happy, even though, you could probably just Google the answer, you happen to be there, and construct a situation in your head where that was a joke. Okay. Next question, how many integers can we form with the numbers 3, 4, 4, 5, 5, 6, 7 if we want our number to exceed 5 million? So as an example, we want, say, the number 5,434,567. That exceeds 5 million, and we've only used each number once. So I just mapped it out, and we want to know how many ways we can do this. So the interesting thing here is that it's not just we pick, okay, let's start with 5 million and arrange the rest however we want. We have to do example by case. So we have to check each individual case. And what I mean by this is we say, what if the first is a 5? Okay, so we have a 5, and then we have 6 other positions. And because our first number is a 5, it doesn't matter what the order of the other 6 numbers are, because it's going to exceed 5 million. So there's going to be 6 ways, or 6 factorial ways, of arranging the rest. But we do have to account for duplicate numbers. So for instance, the number 4 is in there twice, so we have to divide by 2 factorial. And that is the only duplicate number in there. So we have the first is 6 factorial over 2 factorial. I'm not going to shorten that. Okay, so case 2, what if we start with a 6? Well, this is about the same thing, so we have 6 factorial total ways to arrange the remaining 6 numbers. Except this time we have double 4s and double 5s, so we have to divide by 2 factorial twice. And that'll cover all of the cases that this number starts with a 6. And then the last one is the case where the first number is a 7, which actually has the same result as the 6. So now we have to add them all up together. So that's not that bad. We're going to have 6 factorial over 2 factorial plus 6 factorial over 2 factorial 2 factorial plus that same thing. In fact, why don't we just write it like plus 2 times 6 factorial. Now what we can do here is we see that this will cancel to 6 factorial over 2 factorial plus 6 factorial over 2 factorial, which just becomes 2 times 6 factorial over 2 factorial, which of course we can shorten once again just to 6 factorial. So there's some nice simple mathematics, but really I'm going to erase all of this because you don't have to shorten this up in an exam. You just kind of write your pluses and you should be fine. Because this is an exact answer, and the chance that you ever get to use a calculator is going to be very unlikely, and if you do get to use a calculator, you might as well just plug in the values and see what goes on. Anyways, those were some pretty challenging permutation questions. These are definitely ones that you would see on a final, and likely a midterm. I think the circular table question is a very good homework assignment, but I don't think it would come up on an exam unless it was explicitly covered in class, because those ones can be pretty tricky. But hopefully now you have a good grasp of permutations. If not, of course, just leave comments or a specific question you want answered, and I will respond to that as quickly as possible.